Right, we've got a worked example here for transformation of graphs. This is quite an interesting problem, I think. This is about a harbour which experiences a tidal change in water between 4 and 8 meters. The period of successive low tides is every 12 hours and 24 minutes, 12.4 hours, if you like. If a boat has a draft of 5 meters, what proportion of the day can it safely leave and enter? So now a draft of 5 meters basically means that's the depth it needs in order to be able to sail. What proportion of the day can it safely leave and enter? What proportion of total time can it safely leave and enter? We might read this as. Okay, so okay, let's just have a look at this graph. So this gives us a bit of an idea of what the height of the water over time. So it's going to be something like this. It's the question doesn't say, but these things are sort of sinusoidal. So the level of the water goes up, and it comes down, and it goes into this area where there's not enough water available for it for the boat to move, and then back up again. So this is a low tide, this point here, and this is low tide here. So that's the sort of pattern that it follows. Now we actually want to work out the equation for the height of the water. So we're going to start off with a basic sine curve, and then we're going to transform it to take account of the fact that obviously we've got some shifting going on here and some stretching. Okay, let's just have a look at this. If the mean height is 6 meters and varies by 2 up and down, then the height function, which is a function of time, is going to be, well, this is the mean height plus 2 times sine of some function of t. Incidentally, it could be cosine function as well. It just depends how much we're going to shift the curve. So yeah, it's because the sine of some function of t is going to vary between -1 and +1. 2 times that is going to be between -2 and +2, and then if we add 6, that's going to take us between 4 and 8. So it's going to be something. So that's a first shot, if you like, and that's basically given us the, what's happening vertically with this. These are the kind of vertical transformation parameters. But horizontally, what happens horizontally? Okay, so let's have a think about this. So normally when we got the sine curve, a full cycle, which in the terms of this question would be the period between period of successive low tides. So we could pick any 2 points on here to give us a full cycle, but the question is expressing it in terms of successive low tides. So I mean that is obviously the same period as successive high tides, and so on. So the cycle time then is not 2 pi. We want to change it from 2 pi into 12 2/5, which is 62/5 hours. So in order to do that, we're transforming it really from 2 pi t to by dividing by this 5/62. So that's going to give us 5 pi over 31 t. Now, if that doesn't seem obvious to you, well, I'm not too surprised. It's not altogether intuitive, but we can go back and check this anyway. So if we look at obviously if t equals 0 in this function, here's the function. Here's the full function with the 5 pi over 31 t in it. If t equals 0, i.e. the start of our day, if you like, then sine of this is going to be 0. So the height will be 6 meters. That's what we've got on the graph there. Start of time, as it were. We're at 6 meters. Okay, and then which is the mean height. So so to get then to the next mean height, so that's another way of thinking about the full cycle. Not the next mean height, but the next two after, because that is a full cycle. We would have we would need to put t equals 62 over 5. Okay, so that's the full cycle time. So if we put t equals 62 over 5 into this t, then what we're going to get is sine 2 pi, which is 0, and so our height is going to be 6. This bit's going to be 0. So yeah, so every 62 over 5 hours, we're going to get back to our starting point. So so that's a bit of a check. So yeah, what we've done, we've just kind of changed it from 2 pi to 62 divided by 5 by dividing our 2 pi by our 62 divided by 5. Okay, so now what we want, according to this question, is what proportion of the day can it safely leave and enter? All right, so we've got our equation for the height. Well, what we want to find, let's say, are these two adjacent points. This, incidentally, is actually this graph. This is done using Desmos, so we can see from here when t equals 0, we've got a height of 6, yeah, and so on. So we, and we can see on here the cycle time, is between there, the midpoint and the midpoint there. That's 12 point. It looks like it, doesn't it? 12.4 hours. There we go. So that's from mean height going, the tide coming in to mean height, the tide coming in for the next time. That's 12.4 hours. Okay, so we're basically wanting to find the situation where the tide is at 5. If we can find the points in time where the height of the water is 5 meters, then we can calculate this period of time, and then we can compare that to the full cycle and see what proportion of time we're actually able to not navigate, and then conversely that we can navigate. So all right, so in order to do that, what we're going to do is solve this equation. That's going to find these points here. Okay, so that's height of 5 equals this. All right, let's work this through. So if we subtract 6 and divide by 2 from each side, we get this equation. And therefore 5 pi over 31t is equal to 7 pi over 6 and 11 pi over 6. So these would be these would be the corresponding points on an unshifted curve. So we can just use this. We'll go over and do the actual numbers in a moment. So the difference between these two is 4 pi over 6, and that's out of 2 pi. So 4 pi over 6 divided by 2 pi is going to give us a 1/3. So it's a 1/3 of the time is non-navigable for this particular boat. Therefore, 2/3 of the time is navigable. So okay, so that's right. So I've taken a bit of a shortcut there. If you're not convinced by that, let's just work this through then. So we're solving this equation. We've got these two solutions for 5 pi over 31t. These two values. That's what we've shown on the right. And that implies these two values for t. Okay, let's just multiply by 31 divided by 5 pi. So, so the difference between these two is 4 times 31 over 30, or 4.13 hours. Now that's 4.13 hours out of a cycle of 12.4 times. So the 12.4 hours. So the proportion of time that the harbour is not navigable for this particular boat is 4.13 recurring divided by 12.14. That's the full cycle time. This is the non-navigable time. And this is 1/3. So that's 1/3 of each cycle. So and that's the same for every cycle. So 1/3 of the time is non-navigable. Now it does actually say what proportion of the day, but of course that is the same thing. You might have to just have a think about that. But anyway, that's the same thing, 1/3 of each cycle, and therefore the navigable time is 2/3. So we got the same answer that came out of this. So yeah, maybe a bit of a shortcut here to get to the answer, but if you wanted to work it through in detail, that gives you the same numbers. Okay, so that is kind of quite a nice example, and as I say, it's actually effectively modelling the flow of water in a harbour with a transformed sine curve, and the sine curve crops up in all sorts of situations, and so this is a good example. Okay, so hopefully that has been interesting and useful, and see you next time.